Thank you, everyone. I want to thank you for joining us today to talk about a subject that, a lot of people don't like to talk about: air pollution control. When you think about air pollution control and the equipment and the expense associated with it, we don't really add value to your process. We don't reduce cycle times, we don't improve yields, but we allow you to be in compliance with your air permits. So that's one of the things we want to talk about today is, a very high-level discussion on what type of pollution you're going to see from the biochar or the pyrolysis processes, how the various feedstocks impact that, and then we also want to discuss what are the different control technologies and what can you achieve from a control standpoint. Because at the end of the day, if you are over the control limits, the sizing that the federal government, the state, the local regulators require, you're going to have to put in some sort of control technology. So that's what we're going to discuss today. So just a little background on process combustion. I'm sure most of you are not familiar with who PCC is. PCC is an air pollution control company. We've been in business for over 55 years. We're headquartered out of Pittsburgh. We have global operations in Europe, India, and in China. And really what we've done is we cover off on all types of air pollution control technology. So both air and water. We can treat liquid waste as well for very unique special applications. And during the last 4 to 5 years, we've been involved extensively in biochar projects. So from biochar to biocoal, various feedstocks, we have multiple installations in place, and we're also getting heavily involved in the energy to power markets now. So we're taking that technology to that next level, so we're actually generating power. So from an equipment standpoint, when you look at the technologies that PCC is able to offer, we are able to offer direct-fired thermal oxidizers and combustors. So we're going to generate heat sources while we're combusting those pollutants. We have recuperative thermal oxidizers, regenerative thermal oxidizers, all types of scrubber technology, so wet and dry scrubber technologies to treat acid gas formation or other compounds that may be within the waste gas or that gas being evolved from that pyrolysis process. Particulate control, as you're going to see when we get into this presentation, particulate is the #1 compound that needs to be treated throughout the entire process. The biochar manufacturing process. So we can look at bag houses, venturis. If we get into submicron, very fine particulate, we would look at wet electrostatic precipitators. And then the other thing that we really see today, and it's very dominant throughout all industry, you can look at VOCs, volatile organic compounds, those carbon-based compounds that are emitted from various productions. But NOx is nitrous oxide. That is really at almost a higher level from a control standpoint these days. The limits keep going down. The allowable emissions continue to decrease. And depending on where you are in the country, it can be very significant. So we need to look at NOx. We need to look at the alternative technologies that are available to reduce those post-combustion NOx emissions. So we'll be talking a little bit about that as well. So we all know, you're here, you're participating in this conference. We know the benefits of biochar. We know the basic reactions and the basic technology behind pyrolysis. But I'm not sure everybody is really fully aware of what happens during that pyrolysis process when you're at high temperatures, low oxygen contents. Depending on the feedstock materials, you're going to generate various volatile organic compounds, VOCs, NOx, CO, CO2. There's all kinds of things that are coming out of that process. And it's our job to treat those compounds so that you are in compliance and so that we're not polluting the air. So it's one thing to take a waste product and generate something that's very valuable, that has a tremendous amount of value to the market, to the agricultural market, to various industries, for a multitude of applications, but we can't pollute the environment. So the biochar industry is just like any other industry. At certain levels, certain emission rates, you're going to have to put controls in to control the technology. So when we look at a basic layout, you can see in the red circles multiple areas where emissions, VOCs, compounds, items that need to be treated can be found. So, I mean, if you look at the cutters as an example, particulate, you're going to have particulate coming off there. When you get into the dryers, depending on what the feedstock is, the level you're drying, there will be emissions. You will be emitting, along with the moisture that's coming out, typically you're going to be emitting some other compounds. When you get into the pyrolysis, the other sections that are in here, all these are giving off certain compounds. Anything that sees a temperature with this product will emit certain VOCs, certain volatile organic compounds, and they're all going to be based on what that feedstock is. So depending on the feedstock will determine basically what type of emissions and the volume of emissions that you're going to be generating, and we'll go through that in a little bit more detail. So I think when you look at this, the key message here is when you look at the process, throughout that process, you're emitting different things, from particulate matter to VOCs. In certain cases, you'll be generating NOx, CO, CO2. So there are waste products that need to be dealt with. Once again, this is all predicated on where you are from a manufacturing standpoint. What are those tons per year that you're emitting? But if you're in a situation where you have to be controlled, you have to provide control technology, then there are ways of addressing that and meeting probably, I mean, we're meeting California regulations, and they're probably one of the strictest in the country, and we're not having any issue meeting California regulations. So it can be done. When you look at, if you break the compounds down from an emission standpoint, when you look at the entire process as a whole, you can see at the top of the list is PM, particulate matter. So throughout that process, we're giving off particulate, and it can be very large particulate, it can be submicron particulate. So we need to address particulate. When you come down to that next level, you'll see the next one is NOx. So once again, those NOx emissions, those emissions that are coming from nitrogen-bearing compounds. So anything that has a nitrogen molecule in it, when it hits temperature or chemically reacts, you're going to create NOx. Then we get into your VOCs. So those would be all the other types of compounds that are being emitted during the pyrolysis process. CO, SO2, and then in some cases we're going to have acid gas formation. And it can vary. Hydrochloric is very common, depending on what the compounds are that make up that biomass or the product that's going into the system. You could create some acid gas, and those have to be treated. You can't emit hydrochloric acid to the atmosphere. You need to treat that. So when we look at an overview of what are the major emissions, so we talked about particulate matter. Well, particulate matter can come in all sizes. There's a lot of new regulations out there that are taking it down to that PM 2.5, so the very fine, when you're getting into the very fine particulate, and when you get into submicron particulate. And the destruction efficiencies are extremely high, so the requirements are very high. So you have to look at that. And particulate matter can create respiratory problems for people. I mean, you can see it in the air, you can see smoke. Smoke typically has a lot of particulate in it. Volatile organic compounds. So there's all types of compounds that will be released during the pyrolysis process. And you can have compounds such as benzenes, toluenes, xylenes, a lot of different carbon-bearing products. The pyrolysis, there's the PHS, or PAHS products, carbon monoxide, NOx, once again, NOx is critical. And then we've got the HAPS compounds that we have to deal with. So when we look at how do we influence this, we can look at the type of equipment we're using. So what type of equipment is being used for the pyrolysis process? The production conditions. So at what temperature, length of time, oxygen contents, the feedstock type, very critical. What type of feedstock are we using for this? Moisture content within the process. So we need to look very closely at that as well. Feedstocks, all types of feedstocks. You guys, I don't need to tell you what they are. You're all aware of it. There are certain feedstocks that produce less VOCs than others. Typically, when you get into your biomass, your agricultural byproducts, those sort of things, they're very low emitters for the most part. They all emit, but they're very low. When you get into your plastics or your municipal waste, you're going to have all kinds of compounds coming out of those. Municipal waste is probably the worst because you have no idea what's in there. And it varies from municipality to municipality. So if we look at different feed sources, so more or less that biomass, so your barley, your straw, agricultural byproducts, you can see what's emitted. Various compounds are there, but when you get into your plastics and your municipal sludge, you can see all of a sudden now you're dealing with higher concentrations. You have the potential to create acid gas. You also create a lot of NOx. And so this adds to your control requirements. Typically, if we're dealing with particulate matter, we're going to institute baghouses, cyclones, venturis, or if we're into submicron, we're going to go with WESPs. And you could have a combination thereof in some cases. Controlling diverse pollutants. We can do dry sorbent scrubbers, we can do wet scrubbers, carbon injection systems, we can control ammonia slips, so there's a lot of different things like that we can look at. NOx emissions. NOx, once again, is critical, and really it comes down to how effective do we run our process from a control standpoint, and what are you doing in your process to minimize that? Temperature is a big thing. The higher you go in temperature, the more NOx you will generate if you have nitrogen-bearing compounds, so we need to look very closely at that. When you get into advanced gaseous pollutants and typical VOCs, you're going to start to look at wet scrubber technologies, more advanced thermal oxidizers. At the end of the day, the combustion technology, so in the simplest of terms, it's a flame in a can that operates at a given temperature for a given amount of time, typically in the 1 second range at 1650, 1700, 1800 degrees F, you're going to yield very, very high destruction efficiencies. And then if we get into very, very small submicron particulate, we're going to look at wet electrostatic precipitator systems. So here's a chart, and I like to point this chart out because it shows you what the capabilities are of the technologies today that are available for the various compounds that you're going to be dealing with. If we're dealing with particulate matter, we can get down to the submicron removal efficiencies with baghouses in some cases, certainly with WESPs, or some sort of combination thereof depending on the volume and the size of the particulate. You don't want to load a WESP up with huge particulate. You want to save your WESP for that fine, for that polishing. So if you have very large particulate, you're going to deal with that. VOCs, we can achieve 99 to 99.99% destruction via combustion technologies. And there are various technologies out there, various configurations, but you can achieve very high destructions. Carbon monoxide, we can get it down to the 50 part per million range. Sulfur compounds, 98 to 99% destruction. Nitrous oxides, or NOx. We can get NOx down to 80 to 95% removal. Two methods. If we use an SNCR, a selective non-catalytic, we can achieve about 60% reduction. If we use the SCR, the selective catalytic reduction, we can take that down to the 95% range. And then when you look at other pollutants, you can look down the list there, we can achieve very, very high destruction efficiencies. So as I had indicated before, we're really able to provide the technology available to meet the emission requirements pretty much wherever you are. And like I said, we're very successful. We've got 2 installations in California that are meeting all the NOx requirements. So the key is when you are looking at your process and if air pollution control is going to be a requirement, you want to look really, really closely at, number one, your feedstock. What are you going to be doing? What are you going to be using to produce your biochar? And then you want to look at your process. Okay, what can you do from a process standpoint to minimize that? You're not going to eliminate it in your pyrolysis process, but what can you do to minimize that? You need to understand what the composition of that waste gas coming out of that system is. The more information you can provide to the air pollution control supplier, the more efficient and effective and cost effective that system's going to be. Air pollution control equipment is not cheap, and it's an expense. So you want to make sure it's designed to meet the permit, number one, and number two, it's designed to perform day in and day out very efficiently and meet your permit requirements. So when you look at getting ahead of the curve here, you want to look at, once again, your materials of construction. How do you handle varying levels of process change? You need certain levels of flexibility because your process is not going to be the same every day. So you need to understand that when we design the equipment. Design a system that meets all those requirements that are out there. And the other thing that we're seeing a lot of these days, and it really makes a lot of sense, is if you can take that heat that is being generated after you come out of the air pollution control and you can convert that to power. And there are a lot of ways of doing that. You can do that with steam turbines. You can do that with ORCs, organic Rankine systems. And these all allow you the ability to generate power. And you get a return on that investment then. So that power can go to the grid. We have companies we're working with right now that do biocoal. They produce biocoal in California for the steel industry. And they're actually now going to use the off gas and they're going to generate power to power the entire plant. They want to get off the grid. They don't want to pay the high prices. And the other thing we need to think about, today it may not be totally 100% justifiable because electricity is still relatively cheap. We're seeing a lot of the data centers that are coming in. These things require massive amounts of power. And price of electricity in the next 3 years is going to go up. I mean, whether we like it or not, from an industrial standpoint, from a residential standpoint, we're going to be paying more for electricity. So the return on investment is much, much quicker than what it would be today. So you can start to look at this and do a financial analysis and justify this. So I guess in summary, my last slide here, and I think I'm almost on time, really, there's a lot that can be done. This is a great technology. This is a great new industry. And it's been around a while, but it's growing. And it's great to be here and see all the people. We actually have a booth. And, if you have any questions, come by our booth today, booth 201. And we'll certainly talk to you more about any air pollution control needs or the power needs. But you need to be cognizant of it. You need to be aware of it. It's not something anybody really wants to deal with. They really want to do, but you're going to have to do it if you're at a certain size. And I think even if you're small, you're going to want to grow, and as you grow, you're going to hit that level where you're going to be required to permit. And it's nice to know what technologies are available, what options you have, and what can be yielded. So those guarantees that you're going to get. So that was kind of a quick overview and very high-level overview of the technologies. But I guess, in conclusion, the technologies exist. We can hit the permit requirements. There's a lot of flexibility in the different type of technologies that can be selected. So we work very closely. All the systems we do, probably 98% of everything that we do are custom designed. They're designed to meet the specifications that the end user is requiring. So with that, I'll open it up to questions.
Yep, 5 minutes for questions.
Yes, sir.
Michael, great presentation. For dioxins and furans, imagine we bring some plastics in and some other stuff. What do you guys recommend for?
Our standard technology will treat those. I think in the chart, let's see, if I can go back here to that chart. Yeah, those were listed. When you get into the other pollutants, dioxins, furans, we can achieve 99% removal. And it's going to be based on what those compounds are and then how we design the system. There are multiple ways we can design these systems. If we're dealing with high NOx, as an example, we could put a multi-stage system in where we're breaking those nitrogen-bearing compounds down, and we're not treating them with a lot of oxygen. So we would do the same thing when you start to look at dioxins and furans. It all comes down to how do we design that system. So it's more than just a flame in a can. A direct fire thermal oxidizer is basically a burner, a vessel, a flame. You're at a certain temperature for a given amount of time. But there's ways you inject that gas in, that waste in, how you mix it, what the temperature variations. There's a lot of different things that can be done. So we can handle that, yes. It can be treated. Any other questions? Yes, sir.
Yeah, thanks. Based on what you're showing us right here, I'm just curious if you can talk about some of the different fuel stocks that you've dealt with. Selfishly, I'm kind of interested in urban forestry as the feedstock, and so I'm just curious what some of the other common.
The feedstocks that we've primarily worked with have been southern yellow pine. So we're doing applications with southern yellow pine. We're doing it with walnut shells. We're doing it with almond trees. We're doing it with oats. And municipal waste. Those are the ones that we have active programs, active installations going on. Realistically, as long as we know what is coming out, and we're working on a plastics right now, where they're recycling plastics. That one's not in installation, but it's well into the design phase at this point. We need to know what that feedstock is, and we need to know what is going to be emitted from that pyrolysis process. So what is coming out of that after you've put that feedstock in? From that, we will design a system that meets the requirements.
What have you seen from some of those examples of what compounds are coming? Does all of these show up in?
Oh yeah, all of these are going to show up in the various compounds. The more agricultural it is, the less of these compounds we see. When we start to get into the plastics, we get into the municipal waste, that's where we're going to start to see the higher levels of NOx. We're going to see the higher levels of dioxins, furans, and what else was I going to say? Just those tougher to treat compounds. But when you're in the biological, when you're in the wood products, the agricultural waste, they're there, but they're minimal. They're much easier to treat and less requirements. So it's really the plastics and the municipal waste are the tougher of the group that we've looked at.
Time for one more quick question.
Yeah, so I'm just had my head a lot lately in cost estimating, and I'm just wondering if you can provide any kind of rule of thumb numbers or metrics, like in terms of like tons of feedstock processed, or that give project developers an idea of how to budget for what this portion of their project might be? Are we talking 20% of an overall project cost for these kind of like compliance systems, like 30%, 50? I know it often depends, but anything you can
Well,
speak to would be helpful.
Yeah, it depends. That's tough. I mean, honestly, that's very tough. It's certainly something, once we get the data, we can put forth a number very quickly, you know, a budgetary high-level number. I would say, just a guess, the air pollution control portion is probably going to be in the, let's say, for a pyrolysis process that has waste heat capture, and we're going to generate power. The air pollution control portion of that is probably in the range of about 10% of that cost. Okay, if you pull the power out of it, it's going to come down. So it's not overly expensive, but it's all tied to volume. It has to do with how much waste gas are we pushing through there. More than anything else, it's volume. So the bigger the pyrolysis reactor, the more waste you have going through, the bigger the system has to be.